Suppose S is a sample space for a random experiment. We'll denote events defined in that sample space, subsets of it, with letters like capital A, B, C, A1, A2, and so on. And let's consider some operations that one can take with these events. For example, the union. The union of events A and B is written A union B, and this is the set of all points which are in either A or B. In probability language, this means that either A occurs or B occurs, or possibly both. The intersection of two events, A and B, written A intersect B, is the set of all points which are in both A and B, colored yellow in this figure on the right. In probability language again, this means that A occurred and B occurred on the experiment. The complement of a set of an event A is written A bar, and this is the set of all points in the sample space which are not in A, again colored yellow in the figure to the right. The complement of an event A, in probability language, is the event that A does not occur.
This is an applet designed to show what sort of events you can construct as a subset of a sample space S, with only two events, A and B. We started by shading the empty set. You see nothing shaded here. By contrast, if we shade the whole sample space S, then, of course, we obtain everything shaded. Let's now look at two subsets. First, the set A, and second, the event B. A, when you take its complement, you take all the points outside of the event A, that's A complement, and similarly B and B complement. What about the intersection between the sets A and B? The intersection is the set of points that they share, A intersect B. What about the union of A and B? The union is the set of points which are in either A or B or in both. And for example, we can take things like the set of points that are in A but outside of B, A intersect B complement, or B intersect A complement. What happens if we take the points which are outside of A and also outside of B? A complement intersect B complement. What relationship do you see between this set and the set A union B? A union B, A complement intersect B complement. Those two sets are apparently complements of one another. In other words, if you take A union in B, and then you take its complement, the set of all points outside of that union, you obtain the set of all points which are outside of A and, at the same time, outside of B. That's the first of De Morgan's laws, that the complement of a union is the intersection of a complement. And similarly, the complement of an intersection is the union of the complements. Of course, the complement of A is the complement of A, is A complement. The complement of the whole space, the set of all points that are in S but not in S, is the empty set.
There are several laws relating complements, unions, and intersections due to De Morgan. The first says that the complement of a union is the intersection of the complements. A union B, when I take its complement, looks like the yellow region in this figure. It's the region outside of the union. Notice that you can also obtain that by taking the points outside of A and seeking those which are in common with the points outside of B, A intersect and B intersect. If it's outside of A and outside of B, then it's in the complement of the union. Second law can be demonstrated graphically in a similar way. It says that the complement of an intersection is the union of the complements. A intersect B complement is A complement union B complement. And these can be generalized to more than two events. In particular, if I have K events, the complement, again, of their union is the intersection of their complements. And the complement of their intersection is the union of their complements. Mutually exclusive events. Events A and B are referred to as mutually exclusive if their intersection is the empty set, which is to say that they have no points in common. Mutually exclusive events have no points in the intersection. They have no overlap whatsoever. This means that it's impossible for event A and B to occur on the same trial of an experiment. Suppose I have K of events, A1 up to AK. We'll again call them mutually exclusive if no pair, AI and AJ, have any points in common, if the intersection of AI and AJ is empty for all I and J, when I is not equal to J. In general, mutually exclusive events are such that no two events overlap. On the same trial of an experiment, it's impossible to have more than one of these events, A1 up to AK, occurring. A probability set function. Suppose we have some function p which operates on events and associates with an event A a real value, which I'll call p of A, p bracket A. We'll refer to this as a probability set function if it has the following three properties. First, the number associated with every event, p of A, is non-negative, greater than or equal to 0. And that's simply convention. Probabilities that are negative make no sense to us. Similarly, when I look at the sample space S, the set of all possible outcomes from an experiment, the probability of that is equal to 1. And finally, if I have mutually exclusive events, A1, A2, A3, and so on, then the probability of the union of them is the sum of their probabilities. If events are such that no two can occur together, then the probability that A1 occurs, or A2 occurs, or A3 occurs, and so on, is equal to the probability that A1 occurs, plus the probability A2 occurs, plus the probability A3 occurs. The probability of a union is the sum of the probabilities if they are mutually exclusive. If P satisfies these three conditions, these three axioms, we will call it a probability measure, a probability set function, and P of A is called the probability of the event A. These three axioms are the axioms of probability. They're all that's really required to provide a mathematical structure, the calculus of probability, and very sophisticated conclusions. It doesn't matter how those probabilities were assigned. They could have been assigned by a classical definition or a relative frequency definition, or purely subjectively, or by some combination of the two, for example, in weather forecasting. But as long as those three axioms hold, we have a consistent probability model.